It's my pleasure to introduce Abhishek Rathod from Technical University of Munich, and today he'll be telling us about hardness results in discrete Morse theory for two complexes.
Okay. Hello, everyone, and thanks for the introduction and for the opportunity to talk here. So today I'll be talking about some complexity results in discrete Morse theory. This is based on joint work with my advisor, Ulrich Bauer. So let me begin. The plan for talk is that I'll first talk about some preliminaries. I'll recall some elementary notions from combinatorial topology, and then I'll say a few words about complexity theory. And then I'll talk about our contributions, and I'll conclude with the reduction that's used to establish this hardness results. And then I'll talk about the consequences of these hardness results. So, as everyone knows, discrete Morse theory is a combinatorial analog of Morse theory that's applicable to regular CW complexes, and it's actively studied in both pure and applied math. Recall that you call a function on a complex K a discrete Morse function if two conditions are satisfied. One, f is monotonic, and two, for every point in the image of f, the pre-image of f of that point is either a singleton, in which case we call it a critical simplex, or it's a pair, in which case we call it a gradient pair of regular simplices. Now, the collection of all these gradient pairs forms a discrete gradient vector field, which we call V in this picture. Let's do a small example. So in the complex shown below, you have a complex, two complex, and some values assigned to simplices. And as you can check, the pre-image of 6 is this this purple arrow here, so it's a pair, and the pre-image of 5 is this red arrow here. Now, it turns out that for this particular example, the gradient vector field shown here is optimal in the sense that it has the fewest number of critical simplices. But in general, this problem is hard. And just how hard is what we'll see in this talk. So the motivation for studying this problem is that in topology, you are often interested in doing, you often encounter the scenario that you have a large complex and you want to do some topological computations. And it would be convenient to have, let's say, an efficient topologic preserving transformation that takes this large complex to a smaller complex, so that we can perform this expensive topological computations on the smaller complex. Now, discrete Morse theory offers one way to do this, and this is via a theorem by Foreman, which says the following. So if let's say you start with a large complex K with n simplices, and suppose you have a gradient vector field with just m critical simplices, then this large complex K is homotopy equivalent to the small complex K with just m simplices. So in the case when n is large and m is small, you have the situation as above. So let me also briefly recall what is meant by erasability of complexes. So you say that a 2 complex is erasable if it can be collapsed to a 1 complex. So in the example shown below, you can keep collapsing along the free face of the complex until you reach a 1 complex. So this example shows one erasable complex. So as you might already guess from the example, there exists a simple greedy algorithm to check erasability that runs in polynomial time. Now let me recall some notions from complexity theory. So in classical complexity, you have this situation where you are given a graph or a complex of size n, and you want to find, let's say, the optimal solution. And in approximation algorithms, in contrast, what you have is that the goal is a little different. You want to compute not necessarily the optimal, but a solution of cost within some alpha factor of the optimal. And if you want to rule out a polynomial time optimal solution in the classical world, then you often do it by showing that the problem is NP-hard. And the way to do it is to reduce a known hard problem to the problem at hand using so-called polynomial transformations or Karp reductions. And then in the approximation world, what you would do is you would again reduce from a hard problem B prime to the problem at hand A prime using so-called approximation preserving reductions. And now let me say a few words about parameterized complexity. So on the left, you see a decision variant of an optimization problem. And on the right, you see the parameterized variant of the optimization problem. And what you're given here is that you additionally have, along with the instance, that is a graph or a complex, you additionally have a parameter, and which is bounded by some number k. And your R and K are part of the input. And the question you ask is that, can you check if there exists an optimal solution of value smaller than R? And just as philosophically we say that the nice algorithms in the classical world are those that run in polynomial time, in the parameterized world, the nice algorithms are those that run in fk times polynomial of n. So your fk can be an arbitrary function of the parameter k. So it can be exponential, doubly exponential, anything. But what you require is that the dependence on the input size has to be polynomial. So it can be, for instance, it can be, let's say, the graph, the degree or the tree width of a graph. So if that may be bounded. So you want to bound that, and you want to, as long as that is bounded, your algorithm is kind of efficient. So just as you have the class NP here, you have the class WP here, and the kind of reductions that you use here to prove that something is WP hard is the so-called FPT reductions. And in doing so, you basically rule out FPT algorithms for your problem. Now, if you take your optimal solution, the value of the optimal solution itself as a parameter, and you let your R equal to K, then what you get is the so-called standard parameterization of the problem. And most often, this is the most interesting question to ask in parameterized complexity. So this is shown on the left. So you are given again a graph of a complex of size n, and you're asked, okay, your parameter is the value k, which bounds the optimal. And you're asking, okay, can I efficiently find out a solution to this problem? And the rest of the story is the same on the left. But on the right, there is a more refined notion which combines parameterization and approximations. And this is something you would guess. Like, suffice it to say that if you were to combine these notions, this is what you would end up with. But I will not go more into this in the interest of time. So let me talk about the contributions. Say you're given a simplicial complex and you want to compute a vector field on K. There are two kind of questions you can ask. Okay, can I find a gradient vector field with minimum number of critical simplices? And can I find a gradient vector field with maximum number of regular simplices? So if you consider this problem in the classical sense, these problems are the same, because any gradient vector field that minimizes the number of critical simplices will also maximize the number of regular simplices. But from the point of view of approximability, these problems cannot be more different. And in particular, the history of this problem starts with Josvik and Fesch. They showed that computing the optimal gradient vector field is actually NP hard. And they posed the inapproximability questions as open. So, and these are the questions that we'll answer in this paper, in this talk. And one more variant of Morse matchings that we want to consider is the reduced version, where you minimize not the number of critical simplices, but the number of critical simplices minus 1. And again, in the classical sense, this problem is the same as min-mm, but from the point of view of approximability, it is slightly different. So to recap, the kind of questions we're asking is, okay, are there approximation algorithms for this problem? Are there FPT algorithms for this problem? And are there FPT approximation algorithms for this problem? And we study this problem from all three different computational paradigms. And the answer to this question is, for the first question, the answer is yes and no. And for the second and the third question, the answer is no and no. Let me first talk about some related work. So in 2013, Burton showed that a related problem is WP hard in the natural parameter. And they also devised a fixed parameter tractable, but not for the natural parameter, but for the tree width of the dual graph. And then there were some positive results for the maximization variant in 2017. And then in 2019, you had two results where both negative, meaning inapproximability results, both for the maximization and the minimization variant. And what you don't have yet in this picture is WP hardness for Morse matching. You have something for a related parameter, but not for Morse matching. And you also don't have any result for dimension equal to 2. And this is the story we try to complete in this work. So to be precise, the kind of results we have are that for a 2 complex, this problem cannot be approximated within the factor shown here, unless NP is a subset of QP. QP here stands for quasi-polynomial time, the class of problems that can be solved in quasi-polynomial time. And we also show that this problem is WP hard with respect to the standard parameter. We show that there exists no FPT approximation algorithms for any function rho unless WP is equal to FPT. And then finally, we devise n over log n factor algorithm for the minimization problem. Now, we will not discuss the last result in this paper at all, but I'll just say that this basically depends on the fact that the erasability of a complex can be checked in polynomial time. So I'll only talk about a single reduction, and all 3 results, the first 3 results, will follow from this reduction. Now, to reduce a problem, you need a hard problem to reduce from. So this problem comes from circuits. So let's say you are given a circuit in which you have AND gates and OR gates, but no NOR gates, no NOT gates. So only AND gates and OR gates, no NOR, XOR, none of the other gates are there. And what you have, so these are called monotone circuits, and what you want is an input assignment over here that satisfies the circuit. And naturally, this is a directed acyclic graph, so you have a natural predecessor successor relationship. So your Y1 here is a predecessor of Y5, and Y5 here is a successor of Y1. And the problem you're asking is, okay, can you find an input assignment? So can you set these xi's as 0 or 1 so that the circuit is satisfied? But the question is, you want an input assignment of minimum weight. That is, you want fewest number of xi's to be assigned 1. So here is an input assignment. So you assign x0 and x2 as 1. And because you have OR gates here, these gates get satisfied, and then this AND gate gets satisfied, then followed by this, and finally your output gate is satisfied. So this is a satisfying assignment. Now this is not the optimal assignment, because the optimal assignment would simply be setting x4 equal to 1. In general, this problem is known to be NP hard. It's known to be NP hard to approximate within this factor shown here. It's also WP hard, and it also has no fixed parameter tractable algorithms at all. The problem of fan-in circuits, which means that when your AND gates and OR gates have only 2 inputs, is just equally hard. So you can actually start your reduction step from fan-in circuits, not from the one that's shown here. So the reduction follows a 2-step procedure. You first reduce monotone circuits to this reduced version of Morse matching, and then you have another reduction from a reduced version to the absolute version. But in this talk, we'll focus only on the first part, because that's where the ideas are mostly. So what does it mean to have a reduction? So the idea is that you have input instances which are monotone circuits, and you want to transform them to simplicial complexes. And then you have solutions on this side, which are input assignments, and you have gradient vector fields as solutions for reduced Morse matching. And then you want to have a way to go back and forth between the solutions. And this has to be done in a way in which the objective values and the optimal values are nicely related. And this I'll make slightly more precise at the end of the talk. To do this reduction, that is to construct this complex K, you need to start with some building blocks. And the building blocks in our case are based on the so-called Duns hat, which everyone knows, I think. So the idea is that you start with this triangulated complex here, and then you identify this side with this side with this side with the orientation that's shown in the figure. And as most of you would know, that this is a prime example of a complex that's contractible but not collapsible. In particular, the gradient vector field, any gradient vector field for this complex will have at least 3 critical simplices. What we actually desire for our construction is a collapsible complex, but with a fixed number of free faces. So, so over here, you get a complex of that kind. So here you again identify this side to this side to this side, whereas this side remains free. And in this example, you identify this side to this side to this side, whereas the top side remains free. Now, the distinguished edges are shown in color. So you have the source edges S1 and your source edges S1 and S2, and you have target edges here T1 to TL, and you have target edges here T1 to TL. And what we do is to construct this large complex, you identify source and target edges from various building blocks to each other. And then you have this huge complex which has some nice properties. So it's very easy to check that because you have a free face here, you can collapse, you can start a collapsing procedure, and then you can collapse with the whole complex. But maybe what's shown here is, let's say, a canonical gradients for the complexes shown here. And these are the ones that we actually use to assemble a gradient vector field for a large complex. So let me give a brief overview or a high-level description of the reduction. So I'll only talk about the naive attempt, but not the actual construction, because the actual construction is fairly complex for a 20-minute talk. So in the naive attempt, here's what we're trying to do. So you have this circuit that we just saw at this example, and we want to construct a complex whose gradient vector field has as many critical two simplices as the number of input assignments here. Okay, so how do you do this? So to begin with, to every input, to begin with, to every gate, you associate a single dunce hat. And the next step is for every input that is assigned 1 here, you make a simplex in the associated dunce hat critical. So let me show this pictorially. So you have a dunce hat associated to each of the input gates as shown here. And then our assignment was x0 equal to 1 and x2 equal to 1. So accordingly, we made this critical simplex, this simplex critical, and this simplex critical. And now we want to construct a gradient vector field with only these two as your critical two simplices. So the way to do this is as follows. What you do is that in your construction, you identify the target edges of the predecessor dunce hats to the source edges of the successor dunce hats. So as shown in the example here, now I want to implement something like the OR logic, like how do you implement the OR logic as a topology? So what you do is you have your salmon edge here attached to the salmon edge here, and the purple edge here attached to the purple edge here. And the point is that if either of the purple, so now as you can see, the purple edge is not free because it has 1, 2, and 3 critical simplices attached to it. And the salmon edge is also not free because it has 1, 2, and 3 critical simplices attached to it. But now we recall that we made the input this simplex critical. So it is akin to deleting it from the complex. And then you use the canonical gradient vector field that was shown before, and you collapse this guy entirely. And now, although your purple guy is not free, your salmon guy is free. And then, so you see, so this or this has to be satisfied. So here you translate it as this or that can be erased. So if this can be erased, then you can erase away this guy. So this is how you implement OR using, topology. And you can also implement AND using topology. And the way to do it is, okay, so you have, so by induction, you assume that your Y3 and Y2 can be, the source edges of Y3 and Y2 are free. And using that, you want to somehow ensure that Y4, which is an AND gate, is free. So you have dunce hats associated to each of these gates. And then you say, okay, I will collapse Y3 first. And this I can do inductively. And then I collapse Y2 first, second. But you see, originally this blue edge, the source edge, was not free because you had this guy as well as this guy identified here. So it had 5 faces attached to it. But once you do this erasing, this becomes free. And then you can also erase away this guy. So this is how you implement AND using topology. And then this is not enough because you also want to collapse backward. You also want to collapse gates that are actually not satisfied. And to do that, once once you know that your output gate is free or erased, you want to be able to collapse all the gates preceding it. So let's see how to do that. So by induction, you can erase away the dunce hat associated to Y6, and then because of that, you can erase away the dunce hat associated to the output gate. But check here that this guy is attached to the free face here, and so this becomes free now. And you can also erase away the dunce hat associated to X2. So this basically gives you like a procedure to go from input assignments on circuits to gradient vector fields and complexes. But this is somehow not good enough, because for your reduction to be approximation preserving, you need to, for some reason, have not just one but n copies of the dunce hat for non-input gates. And you also need a way to fill in the cycles of it. So your complex is such that it has no true homology, but it has some one homology, and you have to fill away these cycles without affecting the optimal value. And this is the really technical part. So this is achieved in the most simplest manner if you have a predetermined one cycle basis, and then you can fill this one cycle basis in a nice way. And but this creates more complications for us, because to have such a nice one cycle basis, you need an alternative implementation for AND NOR gates. And so I'll not actually talk about the actual construction, which is fairly complex, but I'll only talk about the consequences of the actual construction. The consequences are that you have reduction from monotone circuits to reduced Morse matching, such that this reduction is actually what is called an L reduction, meaning that the optimal values are related by linear inequality, and the difference between the objective value, and the optimal value on the two sides, when you go from here to here, is also related by linear inequality. And in our case, these constants for the linear inequality are 2.5, and since 2 multiplied by half is 1, this is actually what is called as a strict reduction. But there's more. In our case, this is actually an equality. And what's even more, if you actually consider the parameterized version of the problem, this is an FPT reduction. And if you consider the gap version of the problem, this is also a gap preserving reduction. So if you combine all these facts together, what you obtain is that you get the following results for reduced Morse matching. You have this approximation, an approximability result for Morse matching, and you have WP hardness, and you have FPT inapproximability. And then if you follow this one more step, you also get all these results for the absolute version, except that you lose a small inapproximability factor when you go from this step to this step. And final remarks, I'll say that the inapproximability question for manifolds is still open, because the complexes that we construct are not manifolds. And I would like to say that maybe the key technical contribution of this work is that we have a very simple cycle filling procedure, which maybe which someone may learn from and may use in maybe some other combinatorial gadgets. So with that, I'd like to conclude my talk.
Fantastic. Thank you very much, Abhishek. So if everyone will please unmute themselves briefly, let's clap for the speaker. All right, so our first question is from Henry Luo, and he asks, does the order of collapsing matter if there is no symmetry in the circuit topology?
The order of collapsing does not really matter, but we choose a particular canonical order because it's just easier to argue that way. So it doesn't matter how you collapse.
It's very nice. I love the AND gates using dunce caps. That really makes me happy. So I was wondering if you could explain this parameter complexity time a little bit more, this FPT, just because I'm not really, this is my first time seeing it. So you were mentioning how, FPT polynomial, you could have any complexity on F, but P you still want to be a polynomial.
Yeah, exactly.
What are good examples I should think of parameters that are appearing in?
Okay, so maybe suppose it may happen that, let's say your graph has small degree, okay, and you may have, let's say in general your problem is NP hard. So if you just try to solve to find an optimal solution, it's hard because you have no polynomial type solutions. But it may so happen that you may find out that if your degree is small, if your degree is bounded, you may have say exponential or doubly exponential time in the degree, which is not bad because your degree is bounded, and then you may have polynomial time in your solution.
I
But
see.
yeah,
Right.
or let's say something like tree width, or the example that I gave, which is the natural parameter. What if your optimal solution is bounded? So if you have small optimal solution, I think that there are many cases here where if your optimal is small, then you have a fast solution. So it may be exponential, doubly exponential in the value of the optimal, but it's polynomial in the input size.
Right. It allows you to sort of pull out a piece that in many situations you can control, like the degree. Yeah.
Exactly.
So Bae, did you want to ask your question?
Yeah, I was typing. So if you look at the AND or OR gates example where each of the thing has a hat attached to it, right? Is it ordering? You have a specific way how those two hats were glued. Is that
you mean whether you attach this guy or this guy or this guy? You're asking?
Yeah, it seems to be very interesting how you design the gluing procedure. It's completely counterintuitive for me of how like the Y3 gate is attached to the hat attached to the input gate in a very specific way. Can you say some intuition? I mean, if this is a predetermined order, right? This how they are glued. Can you give me some intuition why they are glued this way?
Okay, the idea is that you want to say that if I can erase, so for OR gate, let's say the idea is that normally if there is nothing attached, you can just erase starting from here or starting from here. But what you want to say is that, okay, what if I can't, what if I have something, what if I want to predicate it to something else? Like, then I want to say that this becomes free only if something else happens. So in here, I want to say that this is satisfied, this gate is satisfied only if this has been satisfied. So here you can do like a semantic translation from satisfiability to erasability. So here you say, okay, x2 can be satisfied, so you want to say that this can be erased. And here x1 is not satisfied, so x1 is not erased. So if you see here, you can't start the collapsing procedure from the purple edge because it has 1, 2, and 3 simplices attached to it. But because your orange guy becomes free at some point because of the collapsing, your orange guy allows you to start the collapsing for this guy. Had it been the other way around, you could also have had the case where maybe the orange guy doesn't become free, but the purple guy becomes free. In that case, you would have had the option of starting your collapsing from the purple guy. And if both of them had been free, then you are free to choose where you start your collapse from.
So in other words, that the way those edges are glued together with input and then the gate is such that it somehow respect the underlying logic operation.
Exactly.
Okay. Yeah. Okay, so my second question is that you mentioned in the technical slides, I think one of the slides says technical problem. You mentioned there's some sort of loop you want to fill. That is, again, a little bit lost at me. Where does this one cycle comes from, number one? And, when you say predetermined one cycle basis, can you explain a little bit more? When you say there's one cycles with this without affecting this, where does this one cycle arise?
Yeah. Good question. So I mean, you can see, like, if you just think about how this graph is constructed. So in a way, we are mimicking this graph into a complex. So in a way, this underlying graph itself has some one homology, and when you're doing the attachments, it'll have at least those many cycles because of the way it's glued. I mean, this may not be immediate to picture it, but you can I don't know, spend a few minutes and then you can say that, okay, the topology from this graph already tells you that when you construct this complex, it mimics the connections here. And that's why you also have cycles over there. And once you have cycles there, what happens is that you're trying to control the minimum number of critical simplices, period, not just the minimum number of critical two simplices. And then if your minimum critical one simplices are too many, of the order of n, let's say, then you will not get approximability. So you want your critical two simplices and one simplices to be roughly the same, or rather actually the same. So that's why you have to fill these guys. And so because of Morse inequalities, then you will have you will have no one cycles, and your critical two simplices and one simplices will end up being the same just by the way it's constructed. So that's the intuition of why you'd actually need this cycle filling, because otherwise you will not get you will get a polynomial time reduction. So you'll be able to prove that this is NP hard. But if you also want approximation preserving, this will not hold anymore unless you fill the cycles as well. So that's why you really need this complicated construction.
And to follow up, Henry Luo asks, to follow Bay's question, is there also a canonical way of choosing the spaces of one cycles?
Yes. I mean, not canonical, but here's, maybe I'll go to the extra slides because I have them. Yeah. So what you do is, okay, so what you do is, what you do is you first collapse to the pink guys, okay? So the canonical gradient collapses to the pink guys. And when you assemble all the pink guys, we show that the one cycle basis is supported by the pink edges assembled from all the different building blocks. And then what you do is that, okay, so you fill these pink guys. So you basically find a basis for this intermediate complex. And then you make it upper triangular. So once you make it upper triangular, you can start collapsing from the pivot edge. And that's what you do here. So once you do that, basically you destroy all the cycles because you're collapsing, the pivot away. And what you're left with in the end is like this graph which is supported by the edges in pink. You cannot picture this here, but it's like a big graph that's supported by the edges in pink. And then it's very easy to collapse away rather a tree that is supported by the pink edges. And then any tree can easily be collapsed to a point. And that's the whole idea. Like you first collapse to this pink edges, then you do this. You remove you match away the pivot edge in your basis, because you have an upper triangular basis, and then you finally collapse away the tree that you get. So yeah, that's the idea of cycle filling. So you basically, the way that it's constructed, you have basically an algorithm that already tells you, irrespective of the input instance, you already know where or how your one cycles will fall. They are supported exactly by the pink edges by design.
Any last questions? All right, thanks so much, Abhishek, for the fantastic talk, and thanks everybody for joining today.
Thanks a lot.